Great. Thanks very much to the organizers, and sorry to everyone whose talk I missed yesterday. I'm very happy to be here today. So today I'm presenting on two-step confidence sets and the trouble with the first stage F-statistic. So the kind of starting point for this project is the observation that in contexts where we're kind of concerned about identification, the common approach for empirical research is to proceed in two steps. Right, I'll first try and calculate some statistic which attempts to measure the strength of identification. Think, for example, of the first stage F-statistic in linear IV. If that initial statistic suggests that the usual asymptotic approximations are reliable, everything should be fine, then I'll just proceed as usual and report non-robust confidence sets, say walled confidence sets. If, on the other hand, the model seems to be poorly identified, then I may think about trying to report some sort of robust confidence set. I might seek a new specification, or I might simply decline to report results altogether and just drop the project. For the purposes of this project, I'm going to focus on the case where we always report some sort of confidence set. The reason for this is that the other cases can lead to really terrible properties for reported confidence sets. Right? Just to get a flavor of this, think of a world in which no instruments have any identifying power whatsoever. Right? In that case, purely by chance, I'll still sometimes observe a large value of the first stage F-statistic. But whatever confidence set I report, conditional on observing that value, is still going to be garbage. Right? So here I'm going to focus on the case where if we think that there's an identification problem, we'll report some sort of robust procedure. So to kind of formalize the process I just described, represent the outcome of the first stage using an identification statistic, which I'll denote by phi. Here I'll take phi equals 1 to indicate evidence of weak identification. Based on the outcome of this identification statistic, I'll either then report a non-robust confidence set if identification appears strong, or an identification robust confidence set if identification appears weak. And putting this all together, we can denote the resulting two-step confidence set, which I'll denote by CS2S in this way. Right? It's equal to the non-robust confidence set if phi equals 0, and a robust confidence set if phi equals 1, indicating weak identification. To make all of this a bit more concrete, think about just a simple linear IV model. Right? In that case, we could let the non-robust confidence set be a standard t-statistic-based confidence set using two-stage least squares or limal, and we could let the robust confidence set be an Anderson-Grubin confidence set. In this context, if we let F be the first stage F-statistic, the commonly used Steger and Stock rule of thumb will correspond to taking phi equal to an indicator function for the first stage F less than, for example, 10. Right? For all of these choices, we end up with a two-step confidence set where we report the usual t-statistic confidence set if F is bigger than 10, and report an Anderson-Grubin confidence set if it's less than 10. Now, in this project, my focus is going to be on the coverage of this resulting two-step confidence set. Right? That is, the probability that it covers the true parameter value, which I'll denote by beta naught. Throughout, I'm going to assume that the non-robust confidence set has coverage at least 1 minus alpha under the usual asymptotics. I'll also assume that the robust confidence set has coverage at least 1 minus alpha, kind of regardless of the strength of identification. So the idea here is that this two-step confidence set will be a nominal 1 minus alpha confidence set, where in saying this nominal, I'm ignoring the fact that I'm selecting among these different procedures. And the object I'll be interested in is the maximal distortion of the two-step confidence set, by which I mean the smallest value gamma, such that the coverage of the two-step confidence set exceeds 1 minus alpha minus gamma. Now, unsurprisingly, given all the well-known results on the problems that can arise from pretesting, two-step confidence sets can exhibit large coverage distortions if we choose this identification statistic poorly. What may be a bit more of a surprise to people not familiar with the weak instruments literature is that Stock-Yogo 2005 show that pretests based on the first stage F-statistic can actually be used to bound this sort of coverage distortions if we assume that the errors in the linear IV model are conditionally homoskedastic on the instruments. Right? In particular, Stock and Yogo give a test for example, the hypothesis that a nominal 5% t-test has true size exceeding 10%. Right? And so if we use that sort of pretest, we can bound the coverage distortions that are going to be introduced in this context. Now, one caveat is that the critical values you need to use to get a valid test of that hypothesis are going to be larger than the usual rule of thumb critical value, F equals 10. However, even with this result, there's still a bit of a problem in that we frequently think that economic data is heteroskedastic, serially correlated, clustered, or kind of otherwise deviates from this IID homoskedastic context that you need for this result. So what do I do in this project? So the first thing I do in this project is to demonstrate numerically that the first stage F-statistic is not a reliable measure of identification strength if you relax that homoskedasticity assumption. In particular, I'm just going to show that in linear IV with heteroskedastic errors, you can have enormous values of the first stage F consistent with extremely poor behavior for the usual asymptotic approximations. Motivated by that fact, I'm going to propose a different approach to constructing two-step confidence sets, which will be applicable to general GMM models, will control coverage up to an arbitrarily small user-selected level of distortion gamma when identification is weak, and that will indicate strong identification with probability tending to 1 under the usual asymptotics. So the main idea behind this proposal is that under strong identification, many different procedures are asymptotically equivalent, right? This is of the same flavor as the usual asymptotic equivalence of the trinity of classical tests, right? So in particular, under the usual asymptotics, we can construct a robust confidence set with coverage 1 minus alpha minus gamma that will be contained in whatever non-robust confidence set we want to calculate with probability tending to 1. Thus, in order to assess the quality of the usual asymptotic approximations, it suffices to just compare robust and non-robust confidence sets. And by choosing the identification statistic in this way, I can guarantee that the coverage of the resulting two-step confidence set is bounded below by 1 minus alpha minus gamma for whatever value gamma I pick. Before moving on, I should just talk a little bit about why I'm bothering to think about two-step confidence sets at all. Right? In particular, two-step confidence sets are frequently pretty unappealing from a theoretical perspective. Right? The sort of setting I'm going to be thinking about here is one in which we know how to construct locally asymptotically efficient confidence sets which are robust to weak identification. So from a theoretical perspective, it seems like there's a fairly strong argument that we should just use those procedures all the time. Right? However, first there's a practical problem, which is that that's not what people do. Right? So pretests for identification strength are extremely common in empirical work. And there are a number of reasons for this, right? The usual approximations have advantages in terms of interpretability and work well most of the time. That's why they're the usual approximations, right? However, as soon as we start deciding what approximation to use on the basis of some sort of statistic, we're back in this sort of two-step confidence set world, and so have to worry about these issues, right? And then the point of this paper is that the usual pretests are unreliable, so alternatives are needed. Another take on these results is that one thing I'm highlighting is that robust confidence sets that are efficient under strong identification give a natural, reliable way in which to assess the quality of the usual asymptotic approximations. Right? As a result, you can think of this as a further argument for computing and reporting robust confidence sets, because in addition to giving valid inference, they also automatically give you an assessment of the quality or reliability of the usual approximations. So, just a quick outline for where I'm going to go in the rest of the talk. I'll start by talking about the problems with the first stage F-statistic in more detail. I'll then introduce the simple two-step confidence set I propose, talk to you about its performance in simulation, and say a little bit about how to report results of this sort of procedure. So for the purposes of this talk, I'm just going to focus on the simple linear IV model with a single endogenous regressor. Right? So we have an outcome y, an endogenous regressor x, and a k-dimensional vector of instruments z. For the simulations, I'm going to set the true parameter value beta naught equals 0, and I'll consider two types of calibrations, one with a moderate degree of endogeneity and one with a very high degree of endogeneity. I'll report the simulated coverage of two-step confidence sets, where I'll take the non-robust confidence set, that is the confidence set I'll use when I think identification is strong, to be either a two-stage least squares or limal T confidence set. And I'll take the robust confidence set to be Anderson-Rubin. I'll look at an identification statistic based on the first stage F-statistic, where I'll use the cutoff, either the rule of thumb cutoff 10 or the Stock-Yogo 2005 cutoffs. And the important thing to note here is that these Stock-Yogo cutoffs guarantee coverage at least 85% in the homoskedastic case, regardless of the strength of identification. And again, what I mean by the homoskedastic case is that these instruments, V1 and V2, are conditionally homoskedastic given Z. Finally, for the heteroskedastic simulations, I'll use a heteroskedastic robust form of the first stage F statistic. Unsurprisingly, if you use a form of the first stage F that assumes homoskedasticity, you can get even more terrible performance in that case. So first, I'll think about simulations of the homoskedastic case. So I'm looking at calibrations with moderate endogeneity and high endogeneity, a number of instruments equal to 5, 10, or 20. And then I'm reporting two-step confidence sets using either the rule of thumb or Stock-Yogo cutoffs, which, if I conclude identification is strong, report either limal or two-stage least squares confidence sets. The Stock and Yogo confidence sets are guaranteed to have coverage at least 85% in this case. And we see that that is indeed the case. Right? On the other hand, the rule of thumb for two-stage least squares is not guaranteed to have coverage 85%, but we see that it does fine in the moderate endogeneity calibrations. If we look at the high endogeneity calibrations, we see that we get some larger coverage distortions. But even then, it really only gets severe when the number of instruments is fairly large. Here, I'm repeating the same exercise in heteroskedastic simulations. And we see that the story is quite different. Also, I'm adding two-step confidence sets based on continuous updating or two-step GMM, because liminal or two-stage least squares are asymptotically inefficient in this context, so we might expect different behavior. The main point to note here is that no matter what procedure based on the first stage F-statistic I'm using, all of these two-step confidence sets can have massive coverage distortions in some cases. Right? So this just highlights that if we allow errors to be heteroskedastic, assessing identification strength based on the first stage F-statistic is unreliable. Right? And the real reason for this is that when errors are heteroskedastic, the first stage F just isn't a reliable guide to the reliability of the usual asymptotic approximations. In particular, if I think about the calibrations with 10 instruments, even in the moderate endogeneity calibrations, substantial coverage distortions can persist when the mean of the first stage F statistic is 500. If I allow for a very high degree of endogeneity, things are even more extreme. And I can have large distortions even when the mean of the first stage F is 100,000. So hopefully I've convinced you that if we're going to think about allowing heteroskedastic errors, the first stage F statistic isn't a reliable way to go, so an alternative is needed. So the alternative I proposed is based on the idea of comparing robust and non-robust confidence sets. In particular, in general GMM models, all of the commonly used non-robust confidence sets and any gamma greater than 0, we can construct what I'll call a preliminary robust confidence set, which I'll denote by CSRP, which has coverage at least 1 minus alpha minus gamma, regardless of the strength of identification. Moreover, this preliminary confidence set will be contained in the non-robust one with probability tending to 1 when identification is strong. And I'll choose the robust confidence set such that it always contains the preliminary one. If we then take the identification statistic to be an indicator for the preliminary confidence set not being contained in the non-robust one, right, so we conclude that identification is strong if the preliminary is contained in the non-robust, and otherwise conclude identification is weak, then we can see that under the usual asymptotics, this identification statistic converges in probability to 0. So if the model is well identified, under the usual asymptotics, we'll always conclude that. Moreover, the preliminary confidence set is always contained in the two-step. Right? If the preliminary is contained in the non-robust, I'll use the non-robust. If it's not contained in the non-robust, then I'll use the robust. As a result, the coverage of the two-step confidence set is at least that of the preliminary, which is 1 minus alpha minus gamma, regardless of the identification status of the model. To make all of this a bit more concrete, right, the key ingredient that I require is this preliminary confidence set. So I'll tell you how to construct one in a general GMM model. Right, so consider the usual GMM identifying assumption that the mean of the moment condition is equal to 0 at the true parameter value. In linear IV, for example, this says that the mean of my instruments times my residuals evaluated under the null is mean 0 at the true. For convenience, I'll continue to assume that the dimension of the parameter beta is equal to 1. And I'll let this sigma matrix denote the appropriately scaled asymptotic variance of the moment condition and its derivative. With these definitions, we can define the S-statistic of Stock and Wright 2000, which is just proportional to the continuous updating GMM objective function. And this statistic will converge to a chi-squared k distribution when evaluated at the true parameter value, regardless of the identification status of the model. Following Kleiberg in 2005, I'll also define a statistic D, which is equal to the Jacobian of the moment condition after I've orthogonalized it to the moment condition itself. The k statistic will then just be the appropriately normalized projection of the moment condition onto D. And this statistic will converge in distribution to a chi-squared 1, regardless of the strength of identification. Now, the reason this k statistic is interesting for my purposes is that it's locally asymptotically equivalent to a walled statistic under the usual asymptotics. In particular, under the usual assumptions for W beta, a walled statistic based on an efficient estimator beta hat, we have that the k statistic is uniformly asymptotically equivalent to this walled statistic on neighborhoods of the true parameter value with size inversely proportional to the square root of the sample size. Thus, if we think about this k-statistic confidence set that we get by collecting all the values beta, such that the k-statistic is less than a chi-squared 1 critical value, it'll be asymptotically equivalent to the walled confidence set on root T neighborhoods of beta naught. Now, unfortunately, this equivalence between the walled and K confidence sets holds only locally, not globally. In particular, you can think of this K statistic as a score statistic based on the derivative of the continuous updating GMM objective function. And one consequence of that is that if you think about a well-identified model, the K confidence set will have correct coverage of any local extremum of the population continuous updating GMM objective function. Right? So for example, if your GMM objective has a local maximum, you'll have coverage 1 minus alpha at that point. So to obtain the sort of global asymptotic equivalence that I need under strong identification, I'll need to localize this K confidence set. And to do that, I'll just add, for any constant A, I'll just add A times the S statistic, and consider the preliminary robust confidence set as the set of values such that this linear combination of S and K is less than a chi-squared 1 critical value. Now, this preliminary confidence set has coverage 1 minus alpha minus gamma A, which is equal to the probability that this linear combination of central chi-squareds is less than a chi-squared 1 critical value. And this holds regardless of the identification status of the model. Right, a key point to note here is that gamma goes to 0 as A goes to 0. So I can choose this constant A to attain any desired level of maximal distortion gamma. As long as A is greater than 0, for CSNR, the non-robust walled confidence set, under strong identification, this preliminary confidence set will be contained in the walled confidence set with probability tending to 1. Thus, to assess whether the usual strong identification approximations are reasonable, as I suggested before, we can just check whether this containment in fact happens. And doing this gives coverage for the two-step confidence set at least 1 minus alpha minus gamma. So now that I've made this suggestion, we can think about how it performs in simulation. In particular, for comparability with the earlier simulation results based on the first stage F-statistic, here I'm going to set gamma, the maximal coverage distortion, equal to 10%, so that this two-step confidence set will have coverage at least 85%. And I'll start by considering the homoskedastic case. Right?
Can I just ask a conceptual question?
Yeah.
So, especially given that I'd say most, probably 90% of papers that end up with first stage F-stats less than 10 get thrown away for projects abandoned.
Yep.
And your simulations here are looking at unconditional coverage. Wouldn't it be reasonable, especially with a two-step procedure, to consider conditional inference?
Well, so that's actually exactly, that's basically part of the problem, right? The difficulty is that, think about a world, conditional inference is a big problem, basically. And the reason is that if I'm screening based on the first stage F statistic and only reporting results if the first stage F statistic exceeds 10 or 15 or whatever, that can lead to really terrible properties for the reported confidence sets, right? Like if I'm thinking about a world where there are no where there are no instruments with any identifying power, then those confidence sets will always have terrible coverage, right? And so here, I completely agree that in practice, that's often what happens, right? In some sense, here I'm arguing that it's really a good idea to always report some confidence set, right? For precisely this reason, that if you're doing this screening, the confidence sets that are ultimately reported in the literature can be horrifically unreliable, right? And we wouldn't detect it by looking at the first stage F statistics of published papers, right?
I'm just arguing that in a simulation, if you wanted to capture what seems to be happening in research today, an alternate simulation that might be interesting is saying, what is the coverage conditional on the measured F being greater than 10?
Yeah.
Which is a different experiment when you're doing it.
Right, but so part of the issue is that I need to make sure this is precisely true, but I'm pretty sure you can make that arbitrarily bad if you allow the level of endogeneity to be high, right? Because basically, imagine the true first stage is 0, but that the degree of endogeneity is really high, right? Realizations where I have a large first stage F are going to be those where the first stage residuals are very large in the population. Those will also, by virtue of the high correlation, be ones where the structural residuals are very large in the population. So even if I'm reporting, only an Anderson-Rubin confidence set conditional on the first stage F exceeding 10, I'll still have huge coverage distortions in that case. So yeah, no, I completely agree that screening on the first stage F in the sense of, I'm just going to kill the project if the first stage F is too small is a big problem. Right, I guess part of the perspective of this paper is that since you have robust confidence sets, right, you actually can potentially draw quite informative inferences even in those cases, right? So I would argue that in those cases you should still report the results or bother to calculate a robust confidence set. But if that's not what people do, then yeah, you absolutely get distortions. Unfortunately, that I'm not quite sure how to handle. So if you like, you can say here I'm restricting attention to the case where we always report some confidence set, because in that case, there is a solution that can be pursued, even if it's not what people currently do. Yeah?
So there's another step that's usually done in practice for some of these methods, and that is you look at the GMM criterion function and try to find out if the model's rejected. And if it's not rejected, then you would produce a confidence set, and that is you. I don't know. You go home and do something else. But how does that interplay with this? The possibility that the model's rejected, or basing a test on basing the confidence set on conditioning on looking at whether the reject the restrictions or not.
Yeah. So pretesting based on pretests for kind of correct model specification of that sort. I know there are some papers that show. I think Patrick Guggenberger has a paper that shows that. I think he's looking at a Haussmann pretest rather than the J-statistic pretest. But he shows that basically you can induce massive distortions, again, with that sort of pretest for correct model specification. And so I completely agree that that's a big thing in practice. I'm not really sure how to, don't know of a nice way to prevent that from introducing distortions. It's a very interesting question whether there is one. Any other questions? Great. So now that I've made this proposal, let me tell you a bit about how it performs in linear IV. Right? So again, for comparability, I'll take the maximal coverage distortion equal to 10%. And I'll start by thinking about the homoskedastic case. So as guaranteed by the theory, we see that the two-step confidence sets that I suggest have minimal coverage at least 85%. Something we see that's actually kind of interesting is that in the case with high endogeneity and a large number of instruments, in these particular calibrations, it actually hits that lower bound. So at least in that sense, there's not a ton of slack in this case. Now, one interesting exercise we can do here is that since procedures based on the first stage F-statistic also control coverage distortions, we can just directly compare their performance to that of the procedure I suggest. And in particular, one thing we might worry about here is that the procedure I'm suggesting will just control coverage distortions by always telling you that your model is weakly identified. Right? In that case, you'll always use the robust confidence set and things will look good. But happily, this doesn't turn out to be the case here. In particular, here I'm looking at the Stock-Yogo procedures in blue for limal and two-stage least squares, and my procedures in black, again for limal and two-stage least squares. And I'm plotting the probability that these procedures indicate weak identification against the mean of the first stage F-statistic in the homoskedastic case. And what we see is that the two limal procedures actually perform quite similarly in this moderate endogeneity calibration. For the two-stage least squares procedure, mine is actually somewhat less conservative than the Stock-Yogo procedure in the sense that it's more likely to indicate strong identification for a wide range of values for the first stage F. Now, something that's important to note here is that while a similar result holds in the other moderate endogeneity calibrations, this isn't in general the case in the high endogeneity calibrations. In particular, in the high endogeneity calibrations, these curves cross, so there isn't some sort of overall ranking in terms of conservativeness in these simulations. Now, of course, the whole motivation for my procedures was that they're supposed to control coverage distortions in the heteroskedastic case as well. And here I repeat the same exercise I did in the homoskedastic case, and we see that the maximal coverage distortions of my procedures is bounded by 10%. That is, the coverage is in all cases at least 85%. OK, so just before I wrap up, a little bit on reporting results. So the discussion I've given so far assumes the choice of a particular maximal coverage distortion gamma, right, and proceeds from there. But one issue is that different readers or different authors might not be comfortable with the same choice of this coverage distortion, right? Kind of how bad does the usual asymptotic approximation have to be before you're willing to throw it out? Further, when used at all in empirical work, at least so far as I've seen, robust confidence sets are typically used to supplement rather than replace non-robust ones. Right? So in those cases when someone does report an Anderson-Rubin or some other robust confidence set, it's typically reported alongside the typical t-statistic confidence set, not instead of it. So here I'll think about a modification or a way of reporting results for the procedures I'm suggesting that kind of takes into account both of these points. So in particular, for some gamma min greater than or equal to 0, think about gamma greater than or equal to that gamma min, and define a family of robust confidence sets in this way. Right? So the preliminary confidence set indexed by gamma will be this sort of linear combination confidence set where I use the weight on the S statistic A that gives me that particular gamma. Right? So CSRP indexed by gamma has coverage at least 1 minus alpha minus gamma. Now, something to note here is that these confidence sets are decreasing in gamma. That is, if I think about gamma prime greater than or equal to gamma, the corresponding preliminary confidence set for gamma prime will be contained in the one for gamma. And I'll consider a robust confidence set that contains the preliminary confidence set for gamma min, and thus this entire family. I'll define the maximal distortion cutoff, gamma hat, to be the smallest gamma, such that the preliminary confidence set for that gamma is contained in the non-robust one. Right? So you can think of this as thinking in terms of this two-step confidence set setup that I've been using. Right? This is the smallest level of coverage distortion I would need to be willing to accept to use the non-robust confidence set for this realization of the data. Right? And so what we can do is we can report a non-robust confidence set, a robust confidence set, and this quantity gamma hat. And if I adopt the rule that I'll use the non-robust confidence set if gamma hat is less than some value gamma star, and we'll use the robust confidence set otherwise, then my personal robust confidence set will have coverage at least 1 minus alpha minus gamma star. Right? So in this sense, you basically give people the option to decide which of these confidence sets you're reporting they want to pay attention to. And subject to using this sort of cutoff rule, that actually does have some sort of property in terms of coverage. To give you a sense of what this looks like, I'll just talk briefly about one empirical example. So Asamoglu, Johnson, Robinson, and Ured studied the relationship between per capita income and various measures of political democracy, and argue that once one controls for country fixed effects, there is no significant relationship between these variables. They consider a number of different specifications, including one which instruments per capita income using the trade-weighted income of a country's trading partners. Cerveletti, Jung, Sunde, and Vischer argue that this zero effect finding lacks considerable heterogeneity across countries, and in particular that the relationship between income and democracy is negative in former European colonies. So what I'm going to do here is just re-examine the identifying power of the trade-weighted income instrument in this particular application. So here I'm looking at 3 specifications, the first of which pools across all countries and corresponds to the specification in Asamoglu et al. Next, I'll look at the one that breaks out the non-colonies and is as in Cerveletti et al. And then I'll look at the one focusing on former colonies. Right? First, look at the first stage F-statistic. Right? We see that in the first and third specifications, it's certainly larger than 10 and is actually also larger than the Stock-Yogo cutoffs. So in this context, even if we use the Stock-Yogo cutoffs, we would be comfortable relying on the non-robust confidence sets. On the other hand, if we look at this gamma hat that I just described, it's over 20% in the first calibration and almost 58% in the second calibration, suggesting that in this context, robust and non-robust confidence sets deliver very different answers. Right? In particular, here, the robust confidence set contains the entire interval from -1 to 1, right? Which is where I restricted the parameter space for basically substantive reasons. A coefficient of 1 means approximately that a 1 standard deviation change in per capita income moves the measure of democracy they consider from the lower bound to the upper bound, and -1 means the reverse. So essentially what we see here is that robust confidence sets contain all empirically relevant parameter values, and thus that if we rely on the first stage F-statistic, we run the risk of drawing a very misleading conclusion about the reliability of this instrument. So just to wrap up, in this project, I show that two-step confidence sets based on the first stage F-statistic can be highly unreliable in non-homoskedastic data. I also propose an alternative approach to detecting weak identification and constructing two-step confidence sets, which both controls coverage distortions under weak identification and is applicable to general GMM models, although today I obviously only talked about linear IV, and which indicates strong identification with probability tending to 1 under the standard asymptotics. While I've framed this discussion using linear combination confidence sets, there are a lot of other identification robust confidence sets you could think about using for this same purpose. Kind of as far as my results are concerned, all of those are fine. And a big takeaway from this is that there's a close connection between efficient robust confidence sets and reliable assessments of the strength of identification. So thank you very much.
So we have a few minutes for questions if anyone feels like that. I'm just trying to make the link with your other paper since I saw it a couple of weeks ago.
Yeah.
So with your other paper, you can get this A of D thing, and you can use this D matrix in order to have a diagnosis of strong, weak identification, right? So wouldn't you say it just dominates even for practically oriented empirical people, just to do your one-step procedure, and if people ask you whether you're in a case of weak identification or strong identification, or record this diagnosis?
So the issue with that, so I completely, so that definitely does give you an assessment of identification strength, right? And one thing you could do is you could compute these robust confidence sets that I'm, kind of the preliminary robust confidence at whatever I'm using here, using the procedures in that paper, right? But as far as specifically calculating this A of D to try and assess the strength of identification for this purpose, you'll get a different A of D for each parameter value you look at, either including or excluding from the confidence set, right? Basically, that paper is sort of a testing paper, and so if you're thinking about constructing a confidence set with it, what you'll need to do is invert it. And then there's a question from how you kind of go from that A of D function to your decision whether to report a robust or non-robust confidence set. If you just always report the confidence set based on the procedure in that paper, then it's great. But if you don't, if you kind of look at this A of D function and then make a decision based on that, unless you're careful, I think you're likely to run into these same sorts of pre-screening issues. And I certainly haven't shown that pre-screening on the basis of that will guarantee that you won't run into problems if you sometimes just decide to report a two-stage least squares confidence set.
So in econometrics, we're really familiar with identification issues. And this paper is obviously about identification in a very critical way. But before I get into the formal stuff, let me start a little bit lighter note about identification, which is germane to my heart anyway. Grace was telling me last night at dinner that there's a famous identification issue in econometrics with the name Hansen that you frequently, normally the way we refer to things in the profession is by last name and year of publication. And so when you see that, there's an identification issue about who wrote it. And typically it's Lars, but sometimes it's someone else. Well, now within econometrics, we're going to have a second identification issue that we're going to see the name Andrews, and we're going to wonder, Andrews the new or Andrews the graybeard, that sometimes maybe we should move on to different methods of identification of papers, but that is the technique we use. So anyway, this was a great conference and a really fun paper to read. So to summarize briefly what Isaiah was talking about, his method applies to nonlinear GMM. I won't say general GMM, but GMM settings. But let's focus on the linear classic weak ID case. So y equals x theta plus e. Think of theta as being a scalar, although you could have it being a vector and doesn't change too much. X has instrument z. There's k of them. And the goal is to get a 95% confidence set for theta. I see that the paper is having three main contributions. One, he numerically demonstrates that Stock-Yogo Two-Step fails miserably when there's heteroskedasticity. Second, he proposes a two-step confidence set which has bounded size distortion. And three, I think there's a third contribution, which is he introduces a diagnostic, this gamma hat, which tells us the degree of the non-robust size distortion that we have. So let's review Stock-Yogo Two-Step. This is the 2005 paper published in the volume for Tom Rothenberg. Now, so the classic thing we teach, or at least some of us teach our undergraduate and even our graduate econometric students, is get two-stage least squares theta hat, get a standard error by the standard formula, and then the formula is theta hat plus or minus 2 standard errors, okay, and you report that. Equivalently, you report theta hat and a standard error. Now, if you're a little bit more advanced, you might do Anderson-Rubin. And so the first one is the non-robust confidence set. The second one is the robust confidence set. Everything with Anderson-Rubin is less than the critical value. or we can have other robust confidence sets. Okay, another thing we might do is look at the first stage F-statistic. That was pushed by Stock and Steger early on, and then has been pushed. Now, introduce gamma, which is the maximum size distortion. What Stock-Yogo say is, hey, if you use the non-robust confidence set, if F exceeds a critical value, and the robust one, if F is smaller than a critical value, we can design a critical value function which works in the sense that the maximal size distortion is bounded beneath gamma. It's a really cool result. And it works under homoskedasticity because of the way that the asymptotic theory works. And so that was the work in Stock and Yogo. Now, part of the question in this paper is, suppose we now construct the same Stock-Yogo thing using hetero-robust variances, but use the Stock-Yogo critical values. What happens? Now, in some sense, it's not clear that anything good is going to happen because it wasn't designed for that. But what Isaiah shows numerically is that the coverage is 0%, the size is 100%. You know, that's a pretty clear definition of failing miserably. So, well, how to see that? Or how can we think this in a more progressive way? Go back to two-stage least squares. Suppose we scale things so z prime z is identity. So z prime e goes to a normal. Z prime x goes to a normal plus non-centrality, so that this c and the two z's are normally joint. Then what Stock and Steger show is that beta hat is approximately the ratio of V2 to V1, where V2 is the inner product of these two first random variables, and V1 is the L2 norm on the denominator part. And that fundamental asymptotic result doesn't require doesn't require homoskedasticity or anything else. It just comes from the asymptotic theory that we're going to get this asymptotic representation. Now, where does homoskedasticity come to play? It's that the joint distribution of these two random normal things has a very simple structure. Under heteroskedasticity, those two normal components have a very complicated structure, and it's unclear what is going to be the joint distribution of V1 and V2 under heteroskedasticity. And that is why I think you turn to a numerical result rather than trying to reconstruct the theory for this case. So in the homoskedastic case, what Stock and Yogo show, and this is why they're able to get a very clean result, is that the asymptotic distribution of this ratio of the numerator to the denominator only depends upon k and the concentration parameter lambda prime lambda. So even though lambda is a vector, lambda prime lambda is all that matters. Really cool result. But under heteroskedasticity, that seems not to be the case. Now, I spent some time kind of mulling in my mind, what is the generalization, but I was unable to figure it out in the time I spent thinking about it. I'd like someone to figure it out. So I think one right way to do this would be to ask the question, what would be the correct Stock-Yogo critical values under heteroskedasticity? Could we figure that out? Well, what does weak identification do for us? It's small values of the denominator. Okay, and that's intuitively, that's not mathematically quite right, but it's intuitively. It's small values of this v. So how can we think about v being small? Well, what's its expected value? How can we think about what the expected value is of this denominator? Guess what? It's the F-statistic. The F-statistic, not the hetero-robust F-statistic, but the classic F-statistic is actually an estimator of the expected value of the denominator even under heteroskedasticity. So that suggests that maybe we actually do want to look at the classic F-statistic under heteroskedasticity, but use different critical values because what we're really interested in is two-step. I guess what I'm saying is that, hey, someone out there should write a paper which redoes Stock-Yogo, but does it under heteroskedasticity, and see if you can figure it out. That'd be fun alternative paper. Oh, that's not what Isaiah does. He says, okay, I'm not going to do that. Let's try to be progressive and come up with someone else. So this is what he does. Says, pick gamma. Okay, what's gamma? 10%. But you pick gamma. We're mimicking Stock-Yogo in that we're going to pick a maximum size distortion. And then we're going to have a new statistic. I'm going to call it k sub gamma, which is this linear combination of k and s, where k is the Kleibergen type statistic, and s is an Anderson-Rubin type test statistic. And what's A? A is a function of gamma that we can calculate. Okay? And then we're going to form a preliminary robust confidence interval based on this, which is a function of this gamma. And that is designed to have coverage which is 1 minus alpha minus gamma, so it has kind of smaller coverage probability. Therefore, it's going to be nested within the other one. And then we design a robust confidence interval which uses the kind of the correct critical values, not the bad critical values. And that has coverage which exceeds 1 minus alpha, but could be too conservative. So the two-step confidence interval says use the not robust one, the old-fashioned one. If this preliminary set is a subset of the not robust, use the robust one. If conversely, why is this going to be a good idea? Well, it turns out to be, just kind of by algebra, that the preliminary confidence interval is, strictly speaking, a subset of the two-step, and therefore the two-step must have coverage exceeding that. Therefore, you get this bounded size distortion. But under strong identification, because you had this smaller property by picking gamma to be positive, the preliminary one will be a subset of the not robust. And so asymptotically, the two-step will equal the non-robust confidence set under strong identification. What does that mean? Is that you're going to get its good properties under strong identification. So that's the basic technique he introduced. I guess he probably gave a better job describing it here than I did, but that's the idea. Third thing he does in the paper is introduce this diagnostic, this gamma hat. This is a really cool idea. So what is it? Gamma hat is the smallest gamma such that the preliminary set is kind of gracing or just kind of within the non-robust set. That gives us the ability to report three things. The non-robust classic confidence set, basically theta hat and a standard error. This Anderson-Rubin or this more complicated robust set based on gamma. So actually that's important that the reported two-step confidence robust set is based on this gamma hat and this gamma hat. And then the idea is that you look intuitively at this. If gamma hat is small, the reader is going to focus on the classic confidence set. If the gamma hat is big, you're going to focus on the robust one. And so you kind of win your cake and eat it too. I don't know if you can see this because this is stolen from his paper. Isaiah presented two applications in the paper. He mentioned one in his discussion here. I stole the other one for this purposes because I think this kind of illustrates what's going on. What is this? This is an empirical application none of you have seen before. It's Angress and Kruger, 1991. OK, so we all know that in Angress and Kruger, there's 4 sets of instruments, small getting to big, and things start getting pretty hairy on the right-hand side, okay? But the thing to focus on, so the two-stage least squares estimate are up at top. You know, there are other estimates too, but let's focus on that one. Gamma hat for first specification is 2.5%. So small size distortion means you're happy with the classic confidence interval. Go to the second set. Gamma hat is 18%. So what does that tell you, according to this diagnostic, is, hey, you got size distortion. And so then you might, at that point, you'd want to look at one of the robust confidence sets, which are down here, say the efficient K confidence set, or the two-stage least squares K. So you get a different confidence set. And so that's the point of this work, is that the reader would report all these things. And we have the case 3 and case 4. The case 3, the gamma hat is 58%. Case 4, the gamma hat is 89%. I mean, if you looked at that gamma hat and reported the classic confidence set, you would be kind of crazy. One of the neat things about a discussant is that you can say, hey, gosh, you could do more work, because you don't have to do it. So here's some questions for the future. Confidence sets are the inverse of a test statistic. I mean, to do a confidence set is the same thing as doing testing, but one's the inverse of the other. A good confidence set is constructed by the inverse of a good test. So is this two-step confidence set a good test? I have no idea. Another way of thinking about it is power. So this confidence set, all the paper talks about its coverage probability, but we also want to think about how big it is. That flip side is the power of this. One way to think about this is Stock-Yogo motivated their specific two-step procedure by testing the hypothesis of weak identification, meaning that there'll be a specific size distortion. So we could ask the flip question here. Is this question my preliminary confidence set nested within the non-robust confidence set? That question, is that a good test of the hypothesis of weak identification or weak instruments? I don't know. Maybe this is not really a testing problem, it's really a selection problem, but anyway, it's something to think about here. This is proposing a particular two-step test. It may not be the particular two-step confidence interval that we want in the long run because it's so new. The theory, here's more of a technical issue. The theory concerns these confidence sets when gamma is fixed, but actually what you end up reporting is the confidence set with gamma hat. What are the properties of that? But also, while gamma hat's clever, I still would be interested in knowing some properties of this gamma hat. So for example, do I want to think of gamma hat as an estimate? Is it something that's converging to something? Is it estimating something? Or is it something more like a p-value? So what I mean by that is that when we do classic testing, a p-values are really cool because under the null hypothesis, they can be interpreted as a uniform, a random variable. Is it something like that? I don't know. Might be something useful to think about. This presentation and everything is focused really on the parameter being one-dimensional, but in practice that's not really true. We typically have a large number of coefficients. How do we want to think about that sense? Do we want to think of gamma hat varying across the coefficients? And if that's the case, if gamma hat varies across coefficients, am I using the non-robust confidence set for the returns to schooling and the robust confidence set for the returns to education? Basically the same thing. Returns to experience, something else. Do I want to have, does that make sense? Or do I want to impose some uniformity in terms of this robust versus non-robust across coefficients? That relates to the issue, that relates also to the issue, when we go to confidence sets, comparing a set being nested with another, is that going to make much sense when it's very high dimensional? I have trouble. In one-dimensional cases, I can feel it. In high-dimensional cases, I'm not so sure. So a general comment is when, in the very general context of statistics, when our statistics are non-pivotal, there's no unique method to construct tests, construct confidence sets. One tradition that's very fashionable among young people in our profession these days is to be uniform. And I call it the Berkeley tradition a bit. But it seems like these days, if you don't use the word uniform, you're castigated and as being on the evil or the dark side or something. And sometimes it's phrased in the form of that if you're not uniform, you're not right. That uniform is right, everything else is wrong. Now, there's a pitfall for uniformity, and that it's very conservative. Another pitfall is that it's not clear to me that uniformity is exactly the right decision-making framework. I mean, it corresponds to certain min-max thinking, but it's not clear that it's the correct decision-making. So the statement that it's the right way, it might be a bit strong. This paper instead, along with Stock-Yogo, takes an intermediate or compromise approach that we have a goal for the confidence set, but we're allowing distortion, but we're not going to allow unbounded distortion. We're going to bound the distortion. And so the advantage is that you get tests with good size in the leading case, the cases that we think hold generally, but we're allowing for there to be distortion, but we're going to bound it. I think it's a very useful and practical compromise. It's not uniform. It's allowing a violation of uniformity, but in a bounded way. And I think there's a lot of merit to this approach, and perhaps we should be willing to compromise and allow for non-uniformity as long as we don't allow it to be unbounded. So I'm endorsing that, even though in other parts of my work I've enjoyed kind of trying to stress uniformity.